Distribution of data. To learn a little bit more about how data is distributed and what that really means when we're talking about patient values, you need to know the difference between accuracy and precision. Accuracy, or an accurate result, correctly reflects the true value of the result. So if you imagine a target value that should be obtained for an analyte, accuracy would give you the correct number. Precision occurs when, after repeated analysis, the same result is achieved. So if we run a test 15 times in a row and it's the same sample that we're running 15 times in a row, a very precise instrument would give us the exact same number with every time that we run this analyte. Results can be accurate and not precise, or precise and not accurate, but in a laboratory, we want results that are both accurate and precise. So imprecision means that the values are all over the place. So if we do repeat testing on one patient sample, the first time we could get a 1, the second time a 10, the second time a 5, then a 4, then a 6. So the values on repeat tests are all over the place. That would be imprecise. If we were to have inaccurate results, that would mean that the values we're getting for every sample that we run are just not the correct values at all. Both of those are impacted by quality control. So typically we create reagents in the lab. If those reagents are created incorrectly, it's going to lead to the development of either imprecise or inaccurate results, or both. If we calibrate the instrument incorrectly, that can lead to imprecision. So let's say we were supposed to calibrate an instrument to a certain point, and we did not do that calibration. Well, because we didn't set the correct baseline, all of our results that happen after that are going to be either high or low. They're going to be inaccurate because they're not the correct number, and they're going to be off of where they should be. They're going to be possibly precise. They're all going to be around the same number, but they're going to be inaccurate and not correct. So failing to perform our typical maintenance, our calibration, and our quality control will impact the patient's results. And that's why we learn about precision and accuracy. We got to make sure that everything has been calibrated correctly, reagents have been prepared correctly, and our quality control analytes have been tested along with our patient samples so that we know that we're getting values that make sense. So how do we determine the validity of our data? So one way is by looking at variance, and variance has to do with the range of the data, how far a sample strays from the average of the sample. So if we have an instrument that's no longer reading the results correctly, it's no longer reporting correct results, we may start to see an uptick in variance. So what should be normal samples, we may see that now the samples are getting farther and farther and farther away from what's average. Now sometimes the patient values are the patient values. They're sick, they have something going on, and their values are going to stray from that average. But it's important to know about how wide of a data set we have when we're dealing with certain aspects. Now, if we're dealing with quality control reagents, this is a whole different ballgame than patient samples. With patient samples, we don't know whether they're positive or negative, what value they're going to have in their blood, and they can have pretty much a continuous level of different values. But with quality control, we usually have a positive quality control and a negative quality control. And the positive should be reporting at a certain value. If we start to see a lot of variation in the results that we're getting from our quality control samples, there might be something wrong with the instrument. And then we have to go back and troubleshoot that instrument to make sure that our quality control stays within a particular range. So variance has to do with the precision of a group of numbers, how close together those numbers are to each other. It's represented by this symbol s squared, and it indicates how close together or how precise the numbers are within a group. A group of numbers with a large variance would be expected to have a wide range of values. So this is a data set that ranges from 2 up to 2011. So this is a very wide range. This would have a large variance number. A group of numbers with a small variance would be expected to have numbers that are very close in value. So here we range from 103 up to 106. So those are very tight and close together. The smaller the variance of a group of numbers, the more precise they are. In other words, the more close together those values are. Do we want all patient samples to be close together? Not necessarily. Do we want all quality control reagents to be close together? Absolutely we do. If all of our positive quality control reagents are reading around the same value, then we know that we have a high level of precision, and we're good and comfortable to move forward with then processing patient specimens using that analyzer. So the formula for variance is written here. S squared means variance, the sum of the numbers within the parentheses. XD is an individual data point within the group, and then the mean of the group, and then N is the total quantity of numbers within the group. So just breaking this down, in order to calculate the variance, you would take each individual number minus the mean. So if I have a mean of 2 and I have a data point that's 1, 2, and 3, I would take 1 minus 2 squared, 2 minus 2 squared, 3 minus 2 squared, add those up, and divide by n minus 1, which is 2. So n minus 1, the n is the total number of samples. I said I had a 1, a 2, and a 3. That's 3 samples total. 3 minus the 1 would give us 2. So that is how variance is calculated. Now that was pretty easy to talk through because it was only 3 numbers. Data sets can get really long, so we do have some tools that help us calculate variance, and I'm going to show you how to calculate those variance values really quickly using Excel. It is good to know how to calculate them out by hand, just in case, but you always have Excel available in case you don't remember the equation for variance. So we're going to walk through this example, just showing you an example of variance. So this is our data set. The first thing we did is we ranked the numbers from lowest to highest. So 87 up to 105. Then we're going to find the mean. So finding the average or the mean, that's just adding all the numbers up and dividing by the total number of values. So when we add all of the numbers in the data set up, we get the sum, which is 962, and then we divide it by all of the numbers. So there were 10 different samples that we added up. So we divide 962 by 10, and we get an average of 96.2. Or they rounded it to 96. So now you have to consider each individual result and subtract the result or the mean from each result. So here's a result of 87. So you'd go 87 minus the mean of 96 to give you minus 9. 92 minus 96 equals minus 4. 93 and so forth. So then you would be subtracting the value of each individual result. So, take the result minus the mean to give you a number. So then you would square that. And the reason why we square it is so that we have all positive numbers and it's s squared. So we square it. So negative 9 squared is 81. And then you can kind of go forward like this and see we would just take it squared. Basically, it's minus 9 times minus 9 gives us 81. Now that we have all of these values, we add them together. So when we sum all of these values, we end up with 254. So what that is the top number. So we just calculated the top number. We took each individual value minus the mean, and we squared it. Then we added all of those up. Now we have to take care of the bottom. Well, we had 10 independent samples, so 10 minus 1 gives us 9. So here's the number that we calculated here, 254. 254 divided by 9 gives us 28.2 mgs squared per deciliter squared. So the variance for this group is that. Now, what does that number mean to us? Honestly, not much. So when we look at variance in the clinical laboratory, variance is kind of a stepping stone to the number that actually makes sense, which is standard deviation. Standard deviation is the most frequently used measure of variance in the clinical laboratory. It's just the square root of the variance. So whatever we calculate the variance to be, we take the square root, and that's our standard deviation. So same formula for variation, we just take the square root of it. And the symbol becomes S instead of S squared. So an example, calculate the standard deviation of the following group of glucose values. So note that the variance was already calculated, so all you would do is calculate the square root of the variance. We have 5.3 as our standard deviation. So statistically, if a sample is analyzed 30 times and the mean and standard deviation established for the results obtained, 68.2% of the time, the results would fall within plus or minus 1 standard deviation from the mean. 95.5% of the time, the result would fall within plus or minus 2 standard deviations from the mean. 99.7% of the time, the results would fall within plus or minus 3 standard deviations of the mean. So this is represented by a Gaussian distribution. Mean, median, and mode are all indicators of central tendency. If the mean, median, and mode are all the same number, the group of numbers has a Gaussian distribution, or a normal distribution. Gaussian distribution is a bell-shaped curve where you have an equal number of results above and below the highest point of the bell. So this is what a Gaussian distribution looks like. So if you were to imagine all of the mean of all of the samples and each individual sample, you may get some values here, but then you'd have more and more of the samples falling closer and closer to the mean, and the mean is the highest point of the distribution. So of the population, 68% would be within 1 standard deviation. So if we took the mean and we calculated minus 1 or plus 1 standard deviation from the mean, about 68% of our samples should fall within here out of the population. And this little symbol here, that's the symbol for standard deviation. So we're talking about 1 standard deviation from the mean. And that's standard deviation of a population. So population average, if you remember, I talked about that mu. This is the symbol for the population average, and this is the symbol for population standard deviation. Now, if we go 2 standard deviations away, we've got more of the data included, 95%. And if we go 3 standard deviations away, 99.7% would be within 3 standard deviations. Single rule QC, this means 95% of acceptable results are within 2 standard deviations of the mean. So we typically go as far out as 2 standard deviations. Anything more than that would be considered an unacceptable result. And this is just another diagram showing those percentages on the Gaussian curve. A normal Gaussian distribution has the peak in the middle and looks like a nice bell. Skewed distribution would have a higher number at one end. You can also see a higher number at the other end. So one end is higher or the other end. In a bimodal distribution, you have two peaks. So you have a set here and a set here of the highest numbers. Gaussian distribution and performance. So here's our normal value, plus or minus 2 standard deviations. We've got good performance of the analyzer. If we start to see our values stray way far out from the mean, we have a precision problem. That means our values are popping up all over the place. We're not getting precise results anymore. If we start to see that all of the results are kind of off to one side or the other, we're more concerned with an accuracy problem. So example, if the mean for glucose in a quality control material is 100 mg per deciliter and 1 standard deviation away is 5 mg per deciliter, what is the probability of if the control material is reanalyzed, the result will fall between 95 and 105? Statistically, 68.2% of the time, a result will fall within 1 standard deviation of an established value. How did we get these numbers? So if 100 is our average, and we're saying 1 standard deviation away is plus or minus 5, then we would take 100 minus 5 to get our 95, and we would get 100 plus 5 to get our 105. Now this becomes our range. Now what's the probability of a number falling within our range? At plus or minus 1 standard deviation, the probability is 68.2%. So in this case, if a sample was analyzed 100 times, 68% of the analyses would be between 95 and 105, and 32 would be outside of that range. And that's still considered acceptable. So the standard deviation range is a measurement of dispersion, and it's calculated by subtracting the SD value from the mean value to establish the lowest number in the range, then adding the standard deviation value to the mean value to establish the highest range. So just like I did here, we found out that 5 is 1 standard deviation away. So if our average is 100, to get to a negative 1 standard deviation, we would subtract 5. And that's our 95. That would be the lower end of the range. To get to our plus 1 standard deviation, we would add 5, and that gives us the top of the range, 105. Now, that's our 68% range. That's our 1 standard deviation range. That's all this is saying, except it's written out in kind of paragraph form. Established for quality control material by the laboratory as a method of setting acceptable quality control limits. Frequently, 1, 2, and 3 standard deviation ranges are established. 2 is usually our cutoff. So establishing a standard deviation range, standard deviation intervals, or confidence intervals. So 20 replicates of a single bottle of quality control were analyzed for sodium. The mean is 140. The standard deviation is 3. So to find the range here, you would take the 140 minus 3, so that gives us the lower end of the range. Then you would do 140 plus 3 to give us the higher end of the range. Now, if we wanted to go 2 standard deviations away, we would have to take the standard deviation twice. So here it shows you kind of piggybacking off of the first standard deviation to calculate it. Otherwise, you can just do 2 times the 3 to give you 6. Either way, you're going to get the same number. So 2 standard deviations away, if we start from 1 standard deviation away, you would just subtract an additional 3. Otherwise, if we start at the average, to get 2 standard deviations away, you would have to subtract by 6. So 134 is what you get. If we want to get plus 2 standard deviations away, it would be adding 6 to the average, because 2 standard deviations, if this is 1 standard deviation, 2 would be 6. Same thing with 3. If we had 3 standard deviations away, then we would do 3 times 3, and that would be taking the average and subtracting 9 or adding 9. And those are the same numbers that you get if you do it this method as well. What would be the 1, 2, and 3 standard deviation ranges or confidence intervals for the quality control? So 1 SD range is 137 to 143. 2 would be 134 to 146. 3 would be 131 to 149. So 1, again, these numbers are the percentage values that they would fall within. Coefficient of variation. This is useful when comparing two or more groups of data to determine which has the greatest precision. So let me give you an example. Let's say that we have a new instrument coming in. It's a new analyzer. And we want to see if this new analyzer is more precise and gives us better results. We would take a patient sample or a bunch of patient samples and we would test it, or maybe even a quality control reagent, and we would test it a bunch of times on the old instrument. We would collect that data, we would calculate standard deviation of the data, and then we would calculate the mean. Then from there, we can calculate the percent coefficient of variation. Then we would repeat the same process for the new instrument. We would calculate the standard deviation, the mean, and the coefficient of variation. So calculate the coefficient of variation of the following group. All values have the unit of mgs per deciliter. So the mean would be 96, standard deviation would be 5.3. You would just do the standard deviation divided by the mean times 100%. So the coefficient of variation for this group of values is 5.5. The lower the number, the better the results. So now I'm going to show you how to quickly get descriptive statistics using Excel. So with Excel, you do have to have the data installed on your Excel program. So as long as you have the data and data analysis enabled, you should be able to perform this. If you don't have these two functions in your Excel, you would have to Google how to add those. It's a simple add. You would just go to add-ons and get that. So that you would have to just look up how to add. So what I'm going to do is I put some values in here and I want to know my descriptive statistics for these values. So I would go here and I would highlight my values that I want descriptive statistics for. Then I'm going to go to data analysis. And under data analysis, got a lot of different options here for performing statistics, but I want descriptive statistics. So I'm going to click on that and then I'm going to click OK. Now this brings me here. Now my input range is already highlighted, so that one's good to go. Now I want it going into a new tab, so that's good. And I have to click Summary Statistics. I can also click Confidence Level for the mean. If I want to change the confidence level, otherwise it's automatically set to 95%, and that's where we want to be in the clinical lab. So now that I've clicked Summary Statistics, I can click OK, and bam, there it is in another tab. So from that data set, I now have the mean, median, mode, standard deviation, and variance. Now the rest of these don't come into play too much in the clinical lab. They're good pieces of information, and if you do take a statistics class, this is going to be important for you to know. But those numbers right there are calculated for you, so I still recommend calculating them by hand in case you get a problem on your qualifying exam that asks you to calculate the standard deviation of a data set. They give you an on-screen calculator, and you need to be able to do this by hand. They do not provide you Excel on your qualifying exam. So you should definitely know how to calculate it by hand, but if you want to go and check your work and make sure you got the right value, this is a really fast way to be able to do it.